My name is Mr. David Glante. Some of you may be familiar with me. Today's lesson is going to be on what we call chemical change. This topic is a broad topic that includes rate and extent of chemical reactions. It also includes chemical equilibrium as well as acids and bases. But for today's lesson, we are going to focus on rate and extent of chemical reactions. In the past, they used to call it just rate of chemical reaction, which is okay. Now, according to the ATP, we are supposed to do some revision in grade 10, grade 11 before the grade 12 stuff. So that is what we are going to do. I'm going to divide the lesson into 3 parts, the grade 10 part, the grade 11 part, and the grade 12 part. Now, you shouldn't be scared of this topic. This is one of the easiest topics as far as chemistry is concerned. So I would encourage you to listen attentively and also, subsequently ask questions when the opportunity offers itself. So we start with the grade 10 material. So we're going to talk about chemical reactions and chemical equations. Now, a chemical reaction is simply a process by which reactants combine to form products, or reactants are changed into products. Normally, a chemical reaction is represented by what we call a chemical equation. So, a chemical equation is used to represent a chemical reaction. Now, a typical chemical reaction can be summarized like this. Let me see what's happening to my pen. Oh, my goodness. The pen seems to have a problem. I don't know what's happening. Okay, sorry. So let's proceed. I'm saying that a typical chemical equation can be represented like this. Now, your A and B are collectively called reactants. Reactants. And your C and D are called products. Now, your reactants and your products are separated by an arrow. This arrow there, the arrow here is like an equal sign in mathematics. Remember, in mathematics, you can say 2 plus x is equal to maybe 5. So that equal sign is what we use here as the arrow there. So you have A and B being your reactants, C and D being your products. However, sometimes you may require some specificity. In other words, you want to be very specific and accurate. So you may include what we call state symbols. So for example, under A, you may put a small s here. Under B, you may put AQ. Under C, you may put L. And under under D, you may put G. The S means that A is in the solid state. The AQ means that B is in aqueous solution. When you say something is in aqueous solution, it means that it is dissolved in water. And C means that C is in the liquid state. And obviously, D having a G subscript means that G is in the gaseous state. So this is how chemical equations are written. Now, sometimes this arrow may have something on top of it like this, delta. This delta means that heat is being applied, it's being heated. Okay, heat is being applied. Sometimes the arrow like this may appear like this. This is a chemical equation. An equilibrium, the symbol for chemical equilibrium. But we are not talking about chemical equilibrium now. We are talking about just a normal reaction. So we will talk about chemical equilibrium when we come to a later stage. Now, the ATP requires that we learn how to balance chemical equations. Now, why do we balance chemical equations? We balance chemical equations so that the equations can comply or obey the law of conservation of matter, which says that matter cannot be created or destroyed. In other words, whatever you start with, you must end with it. Science is not magic, okay? So you can't just you start with something and then suddenly the product it disappears. It doesn't show up in the product. It's not allowed. Whatever you start with must appear there. So there are two basic principles pertaining to balancing of chemical equations. The first one is that all the atoms that appear on the left-hand side, in this case, I use the symbol left-hand side, LHS, must appear on the right-hand side. So that is the first principle. The second principle is that the number of atoms on the left-hand side must be equal to the number of atoms on the right-hand side. Now, to do this, you use what we call coefficients. Now, I will explain that. So, for example, if you have one that includes water, let's say you have water here. This is the formula of water. So you are only permitted to write numbers in front of water like this, if it is 2, if it is 3, whatever you want to do. But you do not change the formula of the compound. Some learners are often tempted, they want a quick, uh, you know, resolution of, and then they would try to squeeze something here, maybe 2 here. When you do that, you have changed the formula of this. This is no longer water. It's called hydrogen peroxide. So it is not allowed. It's not permissible. You only write numbers in front like this, sorry, like 2, 3, 4, like that. So we'll demonstrate that very soon. Now, some chemical equations are naturally balanced, means that there is no need to balance them. They are already balanced. So let's look at this first one. In this first one, you have carbon plus oxygen to give you carbon dioxide. The number of carbon atoms on the hand side is 1. So this is 1 here. And there's also 1 carbon atom there, even though we don't write it. It's like in mathematics, you don't write 1x. You simply write x. Everybody knows x means 1x. So what I mean is that there's only 1 carbon atom here. There's also only 1 carbon atom here. The number of oxygen atoms here are 2. The number of oxygen atoms here are 2. So the whole equation is balanced. There is no need to balance them. However, for the majority of chemical equations, you need to balance them. So that's why we're going to look at how to balance chemical equations. Like I said, even though it is in grade 10, the ATP requires that we learn how to balance chemical equations. So let's look at this first one. In the first one, we see that there are 2 hydrogen atoms on the left-hand side. But when you look at the right-hand side, there's only 1 hydrogen atom. So we try to increase it so that they will balance, they will be equal. So we put 2 here. By putting 2 here, the 2 affects the hydrogen and the iodine here. In other words, what I'm saying is that the 2 means that you have 2 hydrogen and 2 iodine, like this. Okay, it's like in mathematics. If you say 2 into brackets x plus y, you're going to have 2x plus 2y. The 2 affects all of them. So when you write something like this, this is what you mean. Now, having written this, now your hydrogen is 2 on the left-hand side here. Your hydrogen is also 2 on the right-hand side. So hydrogen is balanced. Iodine is 2 on the left-hand side. This 2 also affects this one, so it is balanced. So when you write it like this, your equation is balanced. Okay? Now let's move to the next example. In the next example, you have hydrogen plus oxygen to give you water. Now, if you look at the number of atoms of hydrogen, there are 2 atoms of hydrogen here, and there are also 2 atoms of hydrogen here. Okay? So hydrogen is temporarily balanced, only temporarily. Okay. Then we look at oxygen. There are 2 oxygen atoms here, but there's only 1 here. Now, someone will be tempted by saying that, why don't we just write hydrogen, water like this, and then we put 2 here, and then it will balance? I said, you don't do it like that. It is not allowed. You're only allowed to write numbers in front here. So if we want to increase the number of oxygen atoms on the right-hand side, we place 2 here. Now the 2 affects all of them. So the oxygen is 2 and the hydrogen is 2 times 2, which is 4. So you have to come and write 2 here. And then your equation is balanced. Okay? So let's move to the next one. The next one is this. Again, you have nitrogen combining with hydrogen to give you ammonia. Now, if you look at the number of atoms here, if you look at the number of atoms of nitrogen here, there are two. Here is only one. So to increase it, we put two here. And like I said, by writing two here, the two affects all of them. So the nitrogen is 2 times 1, which is 2, and then it's 2 in 2. Okay. However, by placing 2 here, you have increased the number of hydrogen inadvertently. Okay. So you have to account for it on this other side, the left-hand side. So it's going to be 2 times 3, which gives you now 6. And therefore, you write 3 here. So that your nitrogen is 2 here, your nitrogen is 2 here. Your hydrogen is 3 times 2, which is 6. And here it is 2 times 3 and it's 6. So it's balanced. So basically, this is it. I mean, there isn't much with respect to that. So let's look at this one too. Again, if you look at this one, you have sodium combining with oxygen to give you sodium oxide. Okay. So you look at your sodium here. You only have one atom of sodium here, but two atoms of sodium here. So you have to increase the number of sodium atoms on the left-hand side. So we put 2 here. Then oxygen is 2 here on the left-hand side, but it's 1 on the right-hand side. So what do? You also increase it, okay? So you put 2 here. Now, by placing 2 in front here, suddenly there's a problem because the sodium is now 2 times 2, which is 4. But the oxygen is 2 times 1, which is 2. Because this is almost like writing 1 there, but we don't write it. So the oxygen is balanced. 2 times 1 is 2. But the sodium has increased to 4. So you have to come and erase this one. You erase this, and then you put 4 here. So it is balanced. 4, 4, 2, 2. So your equation is balanced. So that's all that we have to do as far as grade 10 is concerned. So we move to the grade 11 stuff. Now, let me quickly say that some of the content or the information in grade 11 would appear in metric. So don't ignore it. The real stuff starts from grade 11. So we are going to start with what we call bond energy. Now, we know that every substance, whether it is a compound or a molecule, contains atoms and ions. Those are the constituents, okay? Now, these atoms and ions are held together by what we call chemical bonds. Excuse me, they could be ionic, they could be covalent, metallic bonding. You know chemical bonding in grade 11, okay? Even grade 10, I think. So these atoms are held together so that they don't fall apart. Okay. And therefore, we say that the force that holds them together is an electrostatic force in most of the cases, but then it stores energy. Okay. And the energy that it stores is called bond energy. When you go to university, it is normally called bond dissociation energy. But at this level, it is enough to just say bond energy, and you are okay. Now, because there are different types of bonds, we would have different types of or different energies or different bond energies. The stronger the bond, the greater the energy that is required to break the bond. And you should also understand that the energy required to break a bond is the same energy that is required to form a bond, because we have what we call the law of conservation of energy, which is energy cannot be created or destroyed, but may be changed from one form to the other. So here you have just a list of what I would refer to as bond energies. The syllabus does not require you to cram. Don't cram this. Okay. These are just information for you to see. This is actually supposed to be a bond like that, not two dots, but because I couldn't type it, that's how it is. So these are the bond energies. Just get used to the fact that they are bond energies, and that's about it. You don't have to bother yourself so much. Okay, now we are going to talk about the energy changes in chemical reactions. Now, as I alluded to when I started teaching in the grade 10 stuff, I said that a chemical reaction occurs when reactants are changed into products. Okay. Now, it may appear very simple to everybody. Reactants combine to form product. That is it. But in actual sense, there are a lot of things that go on that we cannot see with our eyes. And the steps are three. The first one involves the breaking of existing or old bonds. Like I said, every substance contains a bond. So if you are going to react one substance and the other, you first have to break the old bonds before you form new ones. So the first process is breaking of bonds. Now, breaking of bonds requires energy. To break something, even you, if I give you something and I say break it, you have to apply some energy to it. So energy is absorbed from the surrounding into the system to break bonds. So bond breaking requires energy. And therefore, we say it is an endothermic process, not reaction. There's a difference between an endothermic process and an endothermic reaction. So this is a process, just a step. So we call it an endothermic process. Now, after the atoms, ions are free, they have to combine with others to form the product. And in the process of combining to form the product, or when they combine and form the product, energy has to be released. And therefore, we see it is an exothermic process. Exothermic process. So, in other words, what I'm saying is that for every reaction, you have an endothermic process first, followed by an exothermic process. I'm emphasizing the word process, not reaction. Okay. Then we talk about a change in the energy of the system. Now, depending on which is more, if you have more energy absorbed than released during the reaction, we say it is an endothermic reaction. This time we are using the word reaction, not process. So an endothermic reaction is a net reaction. It's like in physics. Let me just illustrate something here. Let's say we have, let me try to squeeze something here. In physics, let's say we are applying a force of 10 newtons here. And then here we are pulling it with maybe 2 newtons, and this one 3 newtons. Okay. The force net, or the resultant force, is going to be the bigger force minus the two smaller forces, 2 plus 3. So this gives you 10 minus 5, and that gives you what? 5 newtons. Okay. So in terms of determining whether something is an exothermic or an endothermic reaction, it is only when the reaction is complete, then you calculate how much heat is coming in and how much heat is given off. Then you do that calculation and determine whether it is an endothermic or an exothermic reaction. I think at another time I will have to, include a real example, something that is different from this one. Okay, so we have that. Then we are going to look at the word enthalpy. Now, the word enthalpy simply means the total amount of energy in a system. Okay, the total amount of energy in a system, the contents of a reaction, the total amount of energy is called enthalpy. But mathematically, we can say that enthalpy is the sum of internal energy and energy available to do work. So enthalpy H is equal to U. This is the internal energy. My handwriting is terrible. And this one is called the energy available to do work. Energy available to do work. Okay, so let me talk about what internal energy is. Internal energy is a bit complex, but at your level, it is acceptable to say that internal energy is just the energy in the chemical bonds. Remember, I said chemical bonds store energy. So the combined energy in all the bonds in a substance, to a large extent, constitutes what we call internal energy. Of course, there's another component, but it will make things complicated. But just remember that internal energy has to do with the number and type of bonds and the energy these bonds store. We call that internal energy. The one that is a bit confusing is this PV, because this is pressure times volume. So how is pressure and volume called energy? Because here it says this is the energy available to do work. So let me do a bit of physics and take you back for those of you who are interested. It's not very necessary, but sometimes I feel that, when you're teaching students, you don't just teach theory, theory, theory. Sometimes it's good to let them know why things happen so that you can appreciate science well. Okay, so P is pressure and V is volume, like you did in grade 11 when you're talking about gas laws, okay? Your Boyle's law, your Charles laws, and so on. So you dealt with pressure and volume. In science, pressure, so this is pressure and this is volume. But before I even deal with this, let me talk about work first. Now, in science, work W is equal to force times distance, okay? The distance can be changed in X or changed in Y or whatever, but let's just use distance, T, for this purpose. Now, distance is a form of length. So instead of writing distance, we can just say work is equal to force times length, because length is distance. Now let's look at pressure. Pressure is equal to, according to physics, I don't know whether your teacher taught you this formula, but I know even in the lower grades, I think grade 7 and grade 8, you did pressure. Pressure is equal to force per unit area. It means force divided by area. Okay? Now, area we know is length times breadth. And instead of using so many symbols, because breadth is also a kind of distance, we can just say it's length. So area is actually length times length. That's why when you calculate area, you use centimeter squared, meter squared, something squared. So we can say the area is L squared, length times length. That is area, okay? So now we are going to look at volume here. And our volume in mathematics, even in the lower grades, you probably learn that volume is equal to length times breadth times height. Okay. So again, breadth and height are also lengths. So you can say volume is equal to length times length times length, because they're all distances. As far as physics is concerned, we don't really distinguish between breadth and height. So we say volume is equal to length cubed. Okay. So let me come here and then we'll see what. Oh, I think it's, look, this thing is not allowing me to, but let me just squeeze something here so that we use the space, because I wanted to do something. So let's try to do it. So we say that our PB is going to be equal to, the P is force divided by area, I said is length squared, times volume is length cubed. So when you cancel this one and this one, you are going to have PV is equal to force times length. And PV is the same thing as force times distance, because distance is also some kind of length. So you realize that this your PV is the same thing as work. Okay? So when you see PV is actually energy or work. So what is the work that they are talking about? So let me again give you a gist of something, if this thing will permit me to, or maybe I should just erase this. Let me erase some of these things so that they don't interfere with how the lesson progresses. Let me erase them quickly. Okay, I think we can use the side. Now, nobody's going to tell you to calculate this thing or to demonstrate it, but it's just supposed to, help you make science more interesting. So, what is this energy available to do work? What does it really mean? If you put something in a container like this, so we have a container like this, you have your reactants here, okay? Especially if they are gases. If they are not gases, it's fine. They exert a pressure in this direction, okay? And the reason they exert a pressure in this direction is because the atmosphere also exerts a pressure on the container. We call it atmospheric pressure. So this component is the component that is used to press against the atmospheric pressure so that the container maintains its shape. That is why, for example, if you drink Coca-Cola or maybe an empty water bottle and you suck the air out of it, you take the air out of it, you see that if the container was like this and there's an opening here and you suck the air out of it like that, it collapses, it becomes something like that. Okay, because there's no air to push against that. So when we talk about the energy available to do work, that is this one. It means that there's some energy in the thing that is pushing the wall in this direction so that it counterizes the effect of what we call atmospheric pressure. So you might perhaps be interested in this, but it's not really necessary. It's just for entertainment purposes, just to enrich the lesson. Okay, so we talk about enthalpy again. We finished defining, writing a formula for enthalpy. It is important to understand that the components of enthalpy cannot be easily determined, especially in a very short time. So, as far as science is concerned, we are not interested in calculating enthalpy. We are interested in calculating what we call enthalpy change or what we call heat of reaction. Enthalpy change is simply the same thing as heat of reaction, which is the heat or the energy of the product minus the energy of the reactant. So basically, that is what enthalpy is, or heat of reaction. So heat of reaction is simply the amount of energy that is absorbed or released during a reaction. Oh, I didn't finish it. Yeah, during a reaction. Okay, so that is heat of reaction for you. Now we are going to look at endothermic and exothermic reactions. Now let me emphasize this again. Like I said, for every reaction, we have both an endothermic step or process and an exothermic process. The overall, when you combine them together, then that will determine whether the whole reaction is endothermic or exothermic. But for every reaction, there's an endothermic step, which is the first one, in which, you know, uh, energy is absorbed from the system to break the bonds. And then when the new bonds are formed, energy is released. That is the exothermic process. Okay. So we're going to look at an exothermic reaction. What is it? It's a reaction in which energy is released to the environment. The temperature of the content or the system together with the surrounding increase. The value of delta H is negative, and new bonds are formed. These new bonds are stronger than the old bonds. I will explain that very shortly. So these are examples of what we call exothermic reaction. Now, I've seen some multiple choice questions, and sometimes they wouldn't. I was teaching a learner last year, and in the same company, and we're going through multiple choice questions. Usually, I don't do that, but for him, it was a one-on-one session, so we did some multiple choice questions. And then they were expecting learners to know that all combustion reactions are exothermic. In other words, if they write something plus oxygen, we call that combustion. And such reactions are automatically exothermic. You don't have to be told in the exam or in the paper that this is an exothermic reaction. You should always know all combustion reaction, any reaction with oxygen is exothermic. Okay. The other exothermic reaction is neutralization reaction. A neutralization reaction is a reaction between an acid and a base to form salt and water. So in the case of this is hydrochloric acid, this is sodium hydroxide, you form sodium chloride and water. So this reaction is called an exothermic reaction. These things, you did them in grade 11. So this is just a a revision. Then we come to what we call endothermic reaction. Now, an endothermic reaction is a reaction that absorbs energy. Okay? It absorbs energy. So the temperature of the system and the surroundings decrease, becomes colder. Delta H is greater than 0. It means that it's positive. And then the new bonds are weaker than the existing bonds or the bonds that are broken. The most popular kind of endothermic reaction is this one, dissolving ammonium nitrate in water. So let me try to explain this statement here where I say new bonds are weaker than old bonds. And then on the other one, I said the new bonds are stronger than the old bond because learners get confused with this. Now, bond strength has to do with what we call stability. And I think for those of you who did technology, if you still remember your technology in grade 7, you are taught something about stability. But let me just use this as an illustration, and then we'll move to something else. Let's say you have two situations. You have a stand like this. This is your ground like this, and then you have this stand as tall as this, and then you put a JoJo tank on it. JoJo tank like this. Okay, this is your JoJo tank. It's called this a JoJo tank. So you have placed it high on this. And then you have another one like this, but then the stand is short, like this. I mean, they're identical. Let me make them identical so that you don't get confused. Assume the stands are the same, except that one is taller than the other. So this is a stand which is identical to the other one. And then you have the same JoJo tank on top of it, like that. Okay. The same type of JoJo tank. Now, if I were to ask you a question, if wind is blowing, assuming they are empty, this is, let's say, about 5 meters, and this is just 1 meter. If the wind is blowing heavily, which one would fall easily? Common sense will tell you that the higher one can fall easily, okay, because of its height. So we say that when substances have high potential energy, they have a tendency of becoming unstable. It means they easily break, they easily fall. So you would see with respect to these diagrams, I'm going to talk about this diagram shortly. This diagram compares, we call this the energy profile diagram. These are called energy profile diagrams, not profile pictures, please. This is a profile diagram. Okay? These are called energy profile diagrams. Now, there's a separate energy profile diagram for an exothermic and an endothermic reaction, and I'm going to explain this again. You did this in grade 11, but for purposes of revision, let's go through it. On the vertical axis or the y-axis, you have what we call potential energy, the same potential energy that I was talking about with respect to this JoJo tank thing. And then this is reaction progress. Reaction progress is just like time. With an exothermic reaction, the potential energy of the reactant is higher than the potential energy of the product. Okay, this is the potential energy of the product. If we take it backwards, it's going to be here. So the product is lower than the reactant, and therefore we say that it's more stable. Now, when something is more stable, it means that the bond is stronger. It doesn't break easily. That's why I use that statement. The lower the potential energy, the stronger the bond. Now, so we have reactants here, we have products here. We have something we call activation energy. The activation energy is the minimum energy that require to start a reaction. So it's the distance from the beginning here to the top. This top is called activated complex. Activated complex, that is this one. So the energy between the reactants to the activated complex or the peak is called activation energy. That is the minimum energy that is required for a reaction to progress. So what is an activated complex? An activated complex is just an intermediate state, okay, between the reactants and the product. It means that you are neither a reactant nor a product. You are in between. I often use this example. If you are cooking pap, you start with maize meal and water. So let's talk about the maize meal. The maize meal is like a solid. So you put it in the water. At some point in preparing it, it becomes semi-liquid, molten. It becomes thick. That thick state is neither your maize meal you started with or the pap that you want to end up with. So it is in between. Yeah, so the same the same concept applies to what we call an activated complex. It is an immediate intermediate or transition state where it is neither a reactant nor a product. So you have that. Now, the difference in potential energy between the reactant and the product, this one here, this difference here, this gap here, when you subtract them, the energy of the product minus the energy of the reactant, that gap is called the heat of reaction, or delta H that I mentioned. Okay, so for an exothermic reaction, your delta H is less than 0, so it means that it's negative. H is negative. And for this one, your delta H is positive. So basically, the diagrams are identical, except that in the case of the endothermic reaction, your products are higher than your reactant. So I want you to look at this diagram very well, and we'll try and answer a few questions. This one, I've already explained it. Said activation energy is the minimum energy needed for a reaction to take place. An activated complex is an unstable transition state between reactants and products. If you don't want the word unstable, you can use intermediate. It's also fine. Okay. So we are going to try our hands on a few questions just to see whether we understand what is going on. This is a question I took from a book. It says that given the following energy diagrams, write the expressions for these concepts using the letters provided in the diagram. A, potential energy of the reactants. So the potential energy of the reactor, remember you always start with your reactant here, and this is your products, okay? So the potential energy of the reactant is from the beginning up to here. So let's assume this is 0. The value here is the potential energy of the reactant. So the potential energy of the reactant is represented by A, and therefore we write A here. So this is A. Okay? So this is A. Then we talk about heat of reaction. The heat of reaction is the difference between the energy levels of the products and the reactants. So this gap here, if you take this one like this to this one, the gap here is your delta H, which is your heat of reaction. So if you move this one like this, you move that one backwards like that, it corresponds to B, this symbol B. That is the gap between that. So we are going to write this one as what? As B. Okay. Then your activation energy. Normally, we say the activation energy is the energy from the reactant to the activated complex. So this is called your activation energy from here to the top. I mean, from the top to the bottom, from here to here. Or it is this one, the same thing. It's the same thing, okay? Or even from here to here, it's the same thing. Okay. Now, but when you look at this diagram, you see that there's no symbol here. There is no symbol here like A, B, C, D. It is left like that. So they want you to use your brains to find out what the activation energy is. Now, if you look at the activation energy, that is the gap from here to here. Okay, just from here like this. Let me put it like this. This is your activation energy like this. Okay, that is this gap. So we can say that since the whole of this from this part up to this part is C, okay? And from this part to this part is A. This is A. So we can say that our activation energy is C minus A. Okay, if you can see it well. Remember A, this A there, if you move it backwards like this, you move the whole of this one here, it's going to stand here. So this is actually A. From here to here is A. And from here, the top is C. So the gap is the difference. So this is going to be C minus A. So the activation energy here is C minus A. Then the energy of the activated complex. The activated complex is on top here. So its energy is the top, the peak, the highest point. So the symbol C is the one that starts from the base, from zero or the beginning, up to the top. So the energy of the activated complex here is C. So we write C here. And then the activation energy of the reverse reaction. The activation energy of the reverse reaction is from here, okay, from here until the reverse reaction means that this one becomes the reactant and that one becomes, and this one becomes the product. In other words, let me put it well. For the reverse reaction going backwards, this one now becomes reactant and this becomes what we call the product. Okay. So if this is the reactant, from the base of the reactant, where the energy level of the reactant is, the potential energy up to the top is called the activation energy. Okay. So the activation energy would be the whole of C here minus D, because D ends here. So the whole of C minus D gives you that. So here we say C minus D. So that brings us to the end of this question. Let's try something else. Uh, this one says that consider the following three graphs. The same scale is used for the course of reaction. Progress of reaction, course of reaction is the same thing. Now it says that which of the three graphs represents an endothermic reaction, and they put an S there. The S means that it could be one or more. So endothermic has the product, the energy of the product should be above the energy of the reactant. So this is an endothermic reaction. This is exo, so this is endo, this is exo, and this is also endo. Okay, so we will say graph, graph one and graph three. So one and three. Now it says that what is the activation energy of each of the reactions? Activation energy is from the reactant to the top, the peak. So for graph one, is going to be the top, the maximum energy there. That is the energy of the activated complex here is 60. So it says 60 minus where the reaction started. The reactant, the energy of the reactant is 20. So that gives you 40. And then you check the units here. The unit is kilojoules. So you write kilojoules. Then you go to the second one. In the second one, the activation energy is from this to the top. So it's going to be 80 is the one on top minus 40. And that gives you 40 kilojoules. Okay. And the third one is from the top 80. The top is 80 minus 20. So this is 80 minus 20. And that gives you what? 60 kilojoules. Okay. So that is that one. Then let's move to what we call calculate the heat of reaction, delta H. So we go back to that. The delta H for each one of them. This one is delta H is going to be this, the distance here. This one is going to be the distance here. Unfortunately, this is interfering, but it's going to be the distance here. So for the first one, your delta H is your product minus the reactant. So it's going to be 40 because of this 40 here minus 20. Okay. And that gives you 20 kilojoules. And this is a positive one because the delta H for endothermic reactions are positive. So you put that as positive. Okay. Now, when we come to the next one, is going to be actually the product minus the reactant. The difference here is going to be the product minus reactant. It's always product minus reactant. So it's the product, the energy at the level of the product is 20 minus 40, and that gives you negative 20 kilojoules. Okay. And then the last one is this one. I can't see. This thing is interfering with it, but let's assume it is also an endothermic reaction, which is going to be the product is going to be 40 minus 20, and that is what? Plus 20 kilojoules. Okay. So that's the relationship between graph 2 and graph 3. If you look at them, you will see that both of them have the same magnitude. The magnitude, I'm not talking about the sign, whether it's positive or negative. I'm talking about only the magnitude. The magnitude of the heat of reactions are the same. So because one is exothermic and the other is endothermic, it means that one is the reverse of the other. So you can say that they are reversible reactions. Okay? You can say they are reversible reactions. We'll talk about reversible reactions when we come to chemical equilibrium in detail, but for now, just take it like that. I don't know whether we need to answer this one. Okay, it says the following diagram illustrates the potential energy diagram for this reaction there. What is the heat of reaction delta H for the reaction that? Now you see that this one is hydrogen plus iodine plus hydrogen to give you hydrogen iodide. And this one is the opposite, is the reverse. So whatever value you have for this, if it is positive, this must be negative. If it is negative, this must be positive. So we come here, the heat of reaction for this one here is giving us negative 21. That is for this one. You see that this reaction is the same thing as this one here. Iodine plus hydrogen to give you hydrogen iodide. So there's a negative sign there. So this one here, your delta H, should be a positive one, positive 21 kilojoules. Then it says here, what is the activation energy for the reverse reaction? The activation energy for the reverse reaction is from here up to here, because this one now becomes the reactant. I told you for reversible reaction, this one becomes the reactant. So from the base to the top, from this to this is like this. This one is like this. So you say 168 plus 21. Activation energy doesn't have a symbol. There is no positive or negative. So you calculate it. I don't have the answer there, but you can just add that. And then what is the activation energy for this reaction, the forward reaction? The forward reaction, the activation energy for the forward reaction is this value here. Because for the forward reaction, this one goes here. Here. Okay, from this base to that. So it corresponds to this value here. So it's 168 kilojoules. Okay? So is the reaction exothermic or endothermic? endothermic or exothermic. It's exothermic because the energy level of the product is lower than the energy level of the reactant. So we say it is exothermic. So basically, this is it as far as it's concerned. Now we are going to talk about rate and extent of reaction. This is the bulk of what you'll be doing in grade 12. Okay, even though I've seen some questions where they ask some of the grade 11's topics, especially multiple choice, what I've taught you before under grade 11, they sometimes ask those questions. But the bulk of the questions come from the beginning of this one, the rate and extent of reaction. Now, the rate of reaction simply means the speed of a reaction, how fast a reaction is progressing, whether it's slow or fast. There are certain reactions that are very, very slow. For example, the rusting of iron. You take a piece of iron and you put it in a dustbin or throw it outside, it rains, a reaction takes place, and eventually you see some browning color. You see some brown, looks like soil on the metal, the iron. We call that rusting. It takes a long time to achieve that. So the process is slow. There are certain reactions that are very, very quick. For example, if you put potassium in water, there will be an explosion. Instant, the reaction is finished. Okay, so the reaction is very quick. So when you talk about the rate of reaction, you are just talking about how fast a chemical reaction progresses, whether it is fast or slow. But as far as a definition is concerned, there are four ways of defining the rate of reaction. In fact, I'll say 8 ways, but we can group them into 4 categories. So if they ask you what is rate of reaction or define rate of reaction, you say that the rate of reaction is the change in concentration of reactants per unit time, or you can say it is the change in concentration of products. So you choose one. Either you say reactants per unit time or products per unit time. So rate is change, the symbol is change, reactants or products divided by time. And then you have change in C, this is concentration time. Remember, concentration is in mole per dm cube. And because it's divided by time, put -1 on top. Okay? Now, you can also define the rate of reaction in terms of moles, not concentration, but number of moles. So we say the rate of reaction is the change in the number of moles of reactants per unit time, or the change in the in the number of moles of products per unit time, just like the other one. So you have change there, change in N over change in T. But this time the symbol is mole and then that per second. You can also look at it in terms of mass. Sometimes certain reactions, especially if gases are produced, the reactant mass decreases over time because the gases are produced and they escape. So you also have change in mass over change in time. The same definition as before. You can also talk about it in terms of volume. Again, change in volume over time. It's also rate of rest. So any definition that suits you. The most popular one is the first one, which is the change in the concentration of the products divided by time. So if that is what you are comfortable with, you should choose them. But I think any one of them is acceptable. If you look at a memo, they will use any one of them. So you are covered in terms of that. Okay. So we are going to look at what we call rate graphs. This one I'm going to draw it. So let's use concentration, for example. So if we have a graph like this and then like this, okay? I'm going to write concentration here. Let me just write Kong. Kong here is concentration for purposes of simplicity. And this is time, okay? The graph looks like this. Oh, and then this one like this, something like that, okay? You can get it in a textbook properly drawn. This graph represents what happens with the reactants. And this one represents what happens with the products. So what do we mean by this? When the reaction progresses, at the beginning of the reaction, the concentration of the reactants are maximum, are at their peak here. But as the reaction progresses, the reactants are used to form products. So their concentration decreases gradually with time, goes down like that. At the same time, the concentration of the product starts from zero because at the beginning of the reaction, products do not exist. So the concentration of the products at the beginning of a reaction is zero. But as the reaction progresses, the concentration begins to increase, and then it peaks like that. So like that. In some textbooks, and this is a more practical approach. Let me forget about this one and draw it somewhere. In some textbooks, they would rather draw it like this. Okay. They'll draw something like this. Okay. And then they'll draw it like this, but it doesn't touch the exact. And then they will draw it like this. And then something like so. This is your concentration, and this is your type. Okay. The reason why it doesn't touch in this case is that they are trying to tell you that not all the reactants are consumed. In other words, the reaction progressed, and stopped, and there were some leftovers. Okay, there were some leftovers of the reactants. Not all of them are used, so it doesn't touch the x-axis or the time axis in this case. So this is very important. When you see them, you don't get confused. Now, whether you calculate the rates using um, the first one, that is reactant or product, there are three stages for each one of them, and I'm going to explain that. Let's use the product first, because that one is easier to see. So let's deal with products here. So this is our time, and this is our what concentration in the case of this. So the pro is like this, goes like this, and slows down like this, and then flattens that. Okay. So there are three stages here. The first part here, from here to here, we say it is fast, or the slope or gradient. Slope or gradient is, we use the word steep. Steep. Okay. Then this one here, between this one and this one, this space here, the slope is, so this one is becoming slow. So we say the slope is a gentle slope, okay, or the slope decreases. Don't want to use that. And this one, sorry, the slope is flat. There's no slope, they actually is zero. Okay. So what this basically means is that at the beginning of the reaction, the concentration of the reactor, I mean the product just shoots up. So it is very fast. So this is very fast. Then it begins to slow down like this, and then it becomes flat. Now, at this point, the moment it begins to become flat, that is when the reaction ends. So if they tell you at what point does the reaction stop, the reaction stops at this time where it begins to be flat, not here. Some learners, for example, they can put 0 here and maybe 2 here and then 4 here, 4 seconds, and tell you at what time does the reaction stop. And the learner will say, no, because this graph ends here, they are going to put 4 seconds. No, it's wrong. Where the graph begins to be flat, that is where the reaction stops. So this is where the reaction stops. Okay. Now you can also look at it in terms of the product, in terms of the reactant like that. Again, you have a quick one. Like, oh, I don't know what's happening with this my technology. Okay, but at least you understand what I'm doing. We have something like this, like that. If you are dealing with the reactants, if this is the concentration and this is the time, it's going to be like that. The first part is very fast, and then it's slow, and then it stops. So the first one is like this one, very fast here. Then this is slow, and then when it becomes flat horizontal here, this is where it stops. Okay, so just take note of that. So this is Very, very important. Okay. Okay. Now we are going to talk about instantaneous rate and average rate. Now, for those of you who do mathematics, this shouldn't be a problem. The instantaneous rate is just the rate taken over a short period of time. So if you have something like this, okay, let's say you have something like this, okay, uh, this is called like this. Let's say this is concentration and this is time, okay? If the graph is like this, and they tell you, so let's say this is 0, this is 1, and this is 2. And they tell you what is the rate at time 1. You take this one like this, and then you locate the position here. Then you draw a tangent. This is something you have done in mathematics. You touch it like this. Okay? Then you draw something like this and draw something like this. Okay? So remember that your rate is equals to your change in concentration over change in time. Okay? So if you did it like this, you look at the concentration here. Let's call this C. We don't have values here, but let's call this C2 and let's call this C1. It's going to be C2 minus C1 over the time. The time period is, in this case, if it is up to this one, we will say 2 minus 0 because this whole thing covers that. I mean, you are familiar with this in maths, you do the same thing. If you are dealing with products, going to be like this. The instantaneous rate is also the same thing. You just draw something like that to meet it at the instant like that, and then you draw your triangle, and then you find it. I mean, this is mathematics. You should know what I'm talking about. So it is the rate at a particular instant where it touches that. So you draw a tangent, we call it a tangent to that one. Then we talk about average rate. Average rate, take it over a period of time. So if you have a graph like this and they say calculate the average rate, maybe between this time and this time. Maybe this is 3, this is 2, this is 1, and this is 0. Okay? So between 1 and 3, just draw a line like this. This is a straight line. Okay? It should be a straight line from here to meet this one. Then you create a triangle out of it, and then you do that. Then you calculate the slope. The slope will be the change in the value. If this is C2 and this is C1, the concentration C1. So the rate is going to be change in C over change in time. So it's going to be C2 minus C1 over your time here. It will be 3 minus 1. Then you calculate and whatever value you get that. Now, so basically that is it. Then we are going to talk about something. But before I even talk about this summary, let me just draw your attention to something because we'll see a number of examples then. If you have a diagram, someone is playing music outside, so let me raise my voice. If you have a diagram like this, okay, two reactions like this, okay, two reactions like this, and then you have let me use this one like this, okay, and then another one like this, and then they ask you which rate is faster. Any rate that is closer to the y-axis, the vertical axis, is always the faster one. So this one is faster than this. Okay, if you are dealing with uh reactants like this, and then another one like this one is faster because it's closer to this axis, the y-axis. So take note of that. So that is all that you should know. Then about the graphs. Then we have a summary there We said the gradient of a mass, volume versus time gives you what we call the rate of reaction, which we have discussed extensively. And the last one is a steeper gradient means a higher rate. So, like I indicated earlier, if you have these two graphs there, this one is a higher rate, because it's closer to the y-axis, and this is a low rate. The rate of reaction is slow. In the same way, this one is high and this one is low. The closer the graph is to the y-axis, the greater or the higher it is. So we are going to end the lesson here by looking at what we call the collision theory. This will lay the foundation for whatever we are going to do. Okay? This will lay the foundation as to what we are going to do. So what is the collision theory? The collision theory attempts to explain what happens when a chemical reaction proceeds. Now, according to the collision theory, before a reaction can progress or can happen, the reactants must combine, they must collide, they must bump into each other, okay, before a reaction can proceed. However, not all collisions, not all bumping into each other are effective. The ones that lead to the formation of products are called effective collisions. I'll talk about effective collisions again the next time I'm going to teach, because I'm wrapping up this. Now, for a collision to be effective, two conditions must be met. One is that the colliding particles must have sufficient energy. In other words, the energy they have must be equal to or greater than the activation energy. So they must bump into each other with a lot of energy. Then the second one is that they must have a proper orientation. Orientation means direction. So let me explain this shortly. Now, orientation means direction. Let me talk to this man. Like I said, orientation means direction. Now, what does it mean in practical terms? Look at this. I'm going to give you an example here. Let's say there's a molecule here, one here, and another one here. If they meet each other like this is called a head-on collision. They are bumping into each other. So this one gives you what we call, um, you know, an effective collision. However, if you have something like this and another one like this, okay, let's say you have something like this, then this one comes in this direction, you have this, just bumps into it like this and goes in that direction, okay? Comes here and goes in that direction. Hey, what's happening? Goes in that direction. You see, it's not head on, okay? It such a collision is not effective. The orientation is bad. So it always has to be in the same plane. If it's the same straight line, must come together and hit each other, and that would cause a reaction too. Okay, so we have spent close 1 hour 10 minutes, and I think it's sufficient for today. The next time, continue, because I think it's too much information. You might get confused. So this is where the lesson ends. Thank you.